Hello and welcome. In this video series, we're going to talk about solving completely coupled FOLSDEs, which stands for first order linear systems of differential equations. So let's recap. So far we've looked at a general system of two ODEs where in general we have no restriction on our functions except that dx dt can potentially depend on x and y, and dy dt can also potentially depend on both x and y. In general, these types of systems can be difficult, if not impossible, to solve using an explicit analytical technique. So solving for x of t and y of t often requires some sort of integration, and these can be pretty difficult to solve. This is especially true when the system is nonlinear, which many models are. So for example, the Lotka Volterra model, which is used to model predator-prey relationships, is nonlinear due to the interaction term r times f. So this is what Lotka and Volterra created or came up with this model that seemed realistic, where the r represents the prey and f represents the predator, think rabbits and foxes. dr dt equals ar minus b times r times f. df dt equals negative cf plus d times r times f, where a, b, c, d are all positive real numbered constants. So the parameters a, b, c, and d, we put negative signs in front of them whenever we want that term to have a negative effect, but a, b, c, and d are all going to be positive numbers themselves. So this interaction term, this rf here, is what makes this nonlinear. And the way you can think about that is it's the product of two dependent variables, and it's as if we have a dependent variable squared. I know it's not totally true because r and f don't have to have the same values, but they're values of the dependent variable. So what can be said about this model? If we can't solve it, what can we say? Where r is the number of prey and f is the number of predators. Well, we can do a little analysis, like say, what happens if there are no prey? So that means r equals 0. Well, if we plug in 0 for r, the negative brf term goes away, and the ar term goes away as well. And so we get dr dt equals 0. For df dt, if we put in 0 for r, then we get df dt equals negative c times f. Well, this is a scalar multiplier of f, meaning that we have ultimate decay in the fox population, and that means the predators are going to die off. In the absence of predators, when f equals 0, well, if we put in f equals 0 into dr dt, we get dr dt equals a times r. And since a is a positive constant, that means the prey are going to thrive. They're going to continue to increase in population size. They're going to just basically reproduce, as we know rabbits do. df dt, if we put in 0 for f in both terms, we get df dt equals 0, which makes sense. We should have no rate of change in the fox population. When r and f are both very large, the non-interaction terms are small, since AR and negative CF are relatively small in comparison to the RF term. So if you imagine R and F are really, really large, and you look at this model, then the AR term will be a lot smaller than the negative BRF term, and the negative CF term will be a lot smaller than the DRF term. And so we can say that these models are just approximately, at least for the moment, equal to just the interaction terms, and that means the prey are going to die off because the predators are really eating them, and the predators are thriving. You can see that's positive d times r times f. And then eventually, this is not permanent, but once the prey die off, then these interaction terms can start to become small again, and then we're back to one of these two scenarios. When we start to lose prey, the predators die off, and so there's this really complex interaction. So we can still obviously conduct a pretty powerful analysis of this system we just did. This is why Lotka and Volterra found these models powerful. And we can also do one other thing, which we haven't described yet, which is to talk about the equilibrium points of a system. Okay, so for a system of ODEs, for the whole set of populations to be in equilibrium, we would expect that both of the rates of change are 0. So in other words, if both dx dt equals 0 and dy dt equals 0, what ordered pairs x and y will cause that to happen? So here I've just replaced r with x and f with y, just to make this a little bit more mathematical. And to find these equilibrium points, all I really have to do is set the rates equal to 0 and solve that underlying system that I get. So here if I set dx dt equal to 0, I'm going to get 1.7x minus 1.1xy. And here I'll get 0 equals negative 0.8y plus 0.6xy. Now we can solve this method using some sort of substitution. This is a nonlinear system, so they can get pretty challenging to solve. But one thing I can do is I can factor out an x from the first equation, and that leaves me with 1.7 minus 1.1y. And I can do something similar for the second equation. I can factor out a y and make this y times negative 0.8y, negative 0.8 plus 0.6x. Now when I solve the first system, I'm going to get two solutions. I'll get x equals 0 because we have a product here. So if x is 0, then 0 times anything is 0. And for the second one, I'll get 1.7 minus 1.1y equals 0. And so that's going to give me y equals 1.7, negative 1.7 divided by negative 1.1, or just 1.7 divided by 1.1. And that's the same thing as 17/11. Now this is an OR statement here. This means either of these two facts could be true in order for the dx dt function to have a 0 rate of change. The second equation, if I solve that one for x and y, here I'll have either y equals 0, because again, 0 times anything will give me 0, or if that second factor, negative 0.8 plus 0.6x equals 0. And so that will give me x equals 0.8 divided by 0.6. And that comes out to about 8/6, or comes out to exactly 8/6. So how do we couple these equations together? Well, in the first equation, if x is 0, that will work. So our EQ points are going to be x and y. So for the first equation, either of these two things can happen. X can be 0 or y can be 17/11. So if x is 0, well, now I need to ensure that the second equation is also equal to 0, and that's going to occur when either y is 0 or if x is 8/6. But if x is already 0 up here, then x can't be 8/6 as well, so the only way for both equations to be in equilibrium is for x to be 0 and for y to be 0. So you can check that. If you plug in 0 for x and 0 for y, you get 1.7 times 0 minus 1.1 times 0, which is 0, and negative 0.8 times 0 plus 0.6 times 0, which is 0. The other way for this to happen is if in the first equation, the other way for the first equation to produce a 0 rate is if y is 17/11. Okay, so if y is 17/11, that'll make the first equation 0. The second equation will only be 0 if y is 0, so that can't be true because we're saying y is 17/11, but it can also still be 0 if x is 8/6. And if you plug in 8/6 for x and 17/11 for y, you're going to get dx dt is 0 and dy dt is 0. So there are actually two equilibrium points for this system, and it's because it's nonlinear that this happens. Now this can become kind of tedious solving these. I thought it would be valuable just to see how one would compute these algebraically, but we can also solve a system like this with Wolfram Alpha, which Wolfram Alpha can do that heavy lifting for us. So all I've input into Wolfram is 0 equals 1.7x minus 1.1xy, comma, 0 equals negative 0.8y plus 0.6xy. And if I scroll down far enough, I'll see the two solutions. Y is 0, x is 0. That matches our equilibrium point that we found first. And then the second one, x is equal to 4/3, y is equal to 17/11. Well, it's the same thing as 8/6. Therefore, we found the exact same solutions. There's also an option to press approximate form if you want to see what these come out to as decimal approximations. So 17/11 is about 1.55 and 4/3 is about 1.33. So what does this mean? Well, this means that the system is in equilibrium. That is, if both populations are ever zero, well, there's not going to be any change in the populations because there's no reproduction, there's nothing happening. And also when x is 4/3 and 17/11, we can sort of think about this as kind of a steady state. A steady state. And that just means that these two population sizes, it doesn't mean that the species are not interacting and that there's not consumption of the prey by the predators, but this is a steady state in that the number of rabbits that die off is equal to the number of rabbits gained, and the number of foxes that die off is equal to the number of foxes gained. And so it appears that the system is not creating any changes in X or Y. The populations are still changing, but there's a zero net change. And so we can think about that as a steady state. So we can actually look at this to see what's going on. I found a pretty good applet. This one here is one that allows, if you select resource number 1 on the following link, you'll get a grapher that you can download, and it makes it really simple to graph the phase plane for the system of differential equations. And so we have the R and the F axes, and we can kind of see that here at 0, 0, it's a little bit difficult to see, but our equilibrium points are 0, 0. So right there, the vectors dx dt and dy dt should be 0 each, meaning there's not going to be any change. And also right around here, there appears to be these like circle of life things going on. And we're going to see in just a moment that right in the center of that is our equilibrium point. That is the 17/11, the 4/3 17/11. So here we could say that is the point 4/3 17/11, and here is the point 0, 0, and those are our two equilibrium points. Let's go ahead and take a look at this grapher and see what it can do for us. So here it is. It looks a little complex at first. It's a little messy, but let's start right at the top. Here we have our display window. So you can see that our first equation is dx dt equals, and you can change this variable if you want to use r. You just have to use a capital R there and make sure that you replace all the x's with r's as well. Same thing for dy dt. You can change it to f and then just replace the y's with f's. But be sure to use these multiplication signs. Otherwise, you're going to get an error. You have to separate every multiplication with a multiplication sign. So here we have our dx dt equals 1.7x minus 1.1xy. And dy dt equals negative 0.8y plus 0.6xy. And here we're just stating the independent variable is t. That should not have to change. Here you can specify your initial time. So we want to start at time 0. And so we can change that to 0. And then t max will just say how far in time do we want to continue on. And that's going to produce this top right graph and this bottom left graph. Then our initial condition here, we can change that to see what the corresponding phase plane or the trajectory will look like. Here, select RK4 system. That's the most accurate one. We'll talk about what RK means. And you can also use Euler, but that's going to be a lot less accurate. And you can see that looks pretty messy. This is the most precise system you can use for graphing. You can just see that here it confirms T final, X final, Y final. You don't need to worry about that. That's just preset by the grapher. This field resolution, this will just change the number of vectors. So if I lower this, you'll just see it shows fewer vectors. I press enter once I input that in, or you can click to another box. 30 I found is pretty good. If you go up to 100, this thing kind of blows up and it looks really, really difficult to read. That just means that we have many, many vectors being plotted, but you can tinker around with that and see what happens. So here what we have is, this is the time domain graph. along this vertical axis, this is x versus t along the horizontal, and this is right here y along the vertical. Oh, I'm sorry, I have this backwards. This is y versus t versus y graph. You can see the labels here. And here is t versus x. Do not worry about this v equals y equals stuff. This is when you're dealing with parameterizations, which we're not going to do. But you can also change the color in here. If you don't like the red, then you can change it to a different color. Now, the one thing I can do in here is I can set my initial condition differently, but I can also drag this curve out, and you can see that changes what initial condition I'm dealing with. So if I want, like, let's say an initial condition out here, I click on that, and you can see that the populations are going to kind of circulate. There's going to be times where x is decreasing, but y is increasing. And now x is still decreasing, but y is decreasing. And now x is increasing, y is pretty flat. And now y is beginning to increase, and then over here somewhere, y begins to bounce back up. Now here you can change, right now we're looking at y between, this is our y-axis, between -10 and +10, and then our x is going from -10 to +10 as well. So you can change those, and you can kind of focus just on the first quadrant. So if we did 0 to 10 here, then we'd only be looking at the x from 0 to 10, and we can do the same thing here, change y from 0 to 10, and we can look at that phase plane. This thing will kind of clunk out a little bit if you make many changes, but there we go. So we can see that as I begin changing that initial condition, again, where my pointer is, that's just the initial condition I'm picking. And as I start to pick rings that are closer and closer, you can see that that point right there is getting closer to some point right in the sort of in the center, if you will, of that spiral. Let me go ahead and clear the initial conditions, and there we go. So we can drag that curve. Now here, this is producing a sketch of the y versus t graph, and down here, sketch of the x versus t graph. So if I come over here and I point right there, you can see in this little box that my t value is pretty much 0, and my y value is 2.87. That's the initial condition that we have right up here. So you can kind of see that the population begins to decrease initially, but then comes back up over time. This is our predator population. Our prey population, right now we have selected as our initial condition at time 0, x is 2.46. And so if I come to this point, you can see that that's about 0, 2.46. So initially it looks like x is decreasing as we move around this circle, or this oval, whatever you want to call it. So the X population, the prey, is decreasing in size until somewhere over here where the population begins to go up again. You can see like right around here, X is not changing very much until it begins to increase again. And then once it hits this point, X begins to decrease again as we move around this oval looking thing. Here, the y value you can see is initially going up, and that's because you can see that the y component of my pointer is increasing until about here, where now the y population begins to decrease, and then there's a real flat portion where there's not much change here in y. That's probably an indicator of this, until y starts to progressively come back up again and then come back down. So we can look at these two graphs. Do not worry about the slide parameter. Do not worry about boxes 2 and 3. You can tinker around with what happens, but let's make one important point here. As I change my initial condition closer to the point of equilibrium, you can see that these curves flatten out, and this guy is almost always right around 1.55. And that was my initial condition for, or my equilibrium point, 1.55 for y. X is about 1.33. So here I should see that all of the x values are right around 1.33, and we can see that in this box here. I can't get the curve to be completely flat because I can't make that point any smaller. Also, if you click on the 0 initial condition, right about there, kind of difficult to do it. There we go. Now you can see that this curve is right at y equals 0 for all time. Again, my pointer, it's hard to keep it perfectly horizontal, but you can see that that y value is always around 0. Same thing here. We should see that x remains pretty close to 0. Again, just because I can't click exactly right there is the reason we see that. So we can see these beautiful plots that we've been sketching by hand based on just seeing the phase portrait of how those populations covary. And you can see that if my initial condition rises, all that does to the y values is now the y values can go really, really, really low or really, really, really high, close to y equals 10. So you can see that right around this point in the curve, the y value achieves about a 10. If y starts at, let's see, about 8.66, right about there, then we can see that y has a massive drop off, very close to 0, as we're traveling along this trajectory, and then y remains pretty flat for a duration of time until that curve comes back up again. It's a little bit of a disconnect here, but that just could be because of the grapher and the quality of the software. So, nonetheless, we just see that as we change the initial conditions to bigger values, we see that those populations, like here x fluctuates pretty much from 0 all the way close to 10, and you can see that on the x curve that point is getting pretty close to 10. That's my max value over here. So we can really see some cool stuff in these phase portraits. So that's a pretty cool analysis that we can do with systems. The question that we have at this point is, what completely coupled systems can we solve? So we're going to restrict ourselves to first-order linear systems of ODEs with constant coefficients. For short, I know this is not short, we call them first-order, constant coefficient, linear systems of differential equations, and we probably should also state that these are homogeneous. And the reason they're homogeneous, so I've just added an H in there, first-order, constant coefficient, homogeneous, linear systems of differential equations, is because they have no plus f of t and g of t. There's no function of time. And if you recall, if there's a function of time added on to the end of these, then that would make this system non-homogeneous. And we can compact this by writing the dx dt dy dt vector as d capital Y dt. So d capital Y dt is just the vector containing the two derivatives as we see here. A is the coefficient matrix A, B, C, D. So A is that coefficient matrix. And the y vector just contains the x and the y. If we lift these off, if we lift up the x and y vectors by using what we know about linear algebra now, we could say that this is dx dt, dy dt, equals our A matrix, which is A, B, C, D, times x, y, which if we recall matrix multiplication, x multiplies the AC vector, producing AX and CX, y multiplies the BD vector, producing BY, DY, and then the result gets added together. So this is just what we're calling the d capital Y dt. This is what we're calling A, and this over here is the non-differentiated dx dt dy dt, which is just capital Y. So, the theorem states that if we compute the eigenvalues and eigenvectors of A and call them lambda 1, lambda 2, v1, and v2, then it follows that the general solution to the system is y equals, vector y equals k1 e to the lambda 1t times v1 plus k2 e to the lambda 2 times v2. And so the way this will end up looking is, remember that y, that contains x and y in it, or x of t and y of t if you want. k1 e to the lambda 1t times v1, that's going to contain two numbers in it. I'm going to call this v11 and v12 for the first component of eigenvector 1, second component of eigenvector 1, plus k2 e to the lambda 2t times v2. v2 is going to contain two components, the first component of eigenvector 2 and the second component of eigenvector 2. And what this will produce is two equations, one which will be k1 e to the lambda 1t v11. So we could write that as v11 k1 e to the lambda 1t. Remember, v11 is just a number. Plus, and here I'll have v21 scaled by k2 e to the lambda 2t. So I'll have v21 k2 e to the lambda 2t. And for the second equation, this is my x of t right here. You can see that that's the first component in this vector. The second component is going to be k1 e to the lambda 1t v12. So v12 k1 e to the lambda 2t, lambda 1t, plus v22, so this number times our k2 e to the lambda 2t. So you can see that both of these are going to be exponential functions. The lambdas could be positive, negative, they could even be complex, but this is what x of t and y of t will look like. So we can think about this as x of t, this whole thing, and we can think about this as y of t. And so we have our solution to that system. K1 and K2 are arbitrary constants as usual, whose values are determined by the initial conditions. X of 0 equals some x value, x naught, and y of 0 equals some y value, y naught. So we'll prove this a little bit later, but let's solve a couple problems first. For now, we're only going to consider situations with real eigenvalues and eigenvectors, and yes, it's possible for these to have non-real, so imaginary components, and even repeating eigenvalues. But let's take a look at a problem that we've explored already that we couldn't solve, a completely coupled problem. We had two species, each of one preys upon the other. Each of the creatures in species 1 eats on average 3 of species 2 each day. So what that meant is species 2, I'll call that dy dt, is negatively affected by the size of the x population. And since there are x of species 1, and each one of those eats 3 of species 2, we wrote dy dt is negative 3 times x. So negative 3 consumed y population values per one of species 1, and dx dt was similar, but dx dt, every creature in species 2 consumes 1.5 of species 1. Now, in order to find the eigenvalues and eigenvectors of this, I have to convert this to a matrix equation. So the first thing I'm going to do is I'm going to write dx dt as 0x minus 1.5y. So because this equation doesn't have x in it, I can write 0x, and I'm going to need that for my coefficient matrix. dy dt has negative 3x in it, and it has 0y in it. So it's important that notice that we wrote dx dt, then dy dt. We need the x variable and then the y variable next. And so this implies that our A matrix is going to equal 0, negative 1.5, negative 3, and 0. And so we now need the eigenvalues and eigenvectors of this matrix. And that is what the theorem is stating, that compute the eigenvalues and eigenvectors of A and call them these quantities. Then it follows that the general solution involves those quantities. So we now go over to Wolfram Alpha. We're going to compute our eigenvalues, and notice how it's input eigenvalues of bracket, open the first row, 0, comma, negative 1.5, close the first row, comma, open the second row, negative 3, comma, 0, close the second row, close the matrix, and we should see our matrix as we have it input. So I get a lambda 1 of about negative 2.12. I've pressed the approximate form button because otherwise it gives you the exact values, and those can look pretty ugly with radicals and all that stuff. And then I have my v1 and v2 here. So my solution is going to be k1 e to the lambda 1t. So lambda 1 is negative 2.12. So we have that here. Times v1. So v1 is the vector 0.71, comma 1. So I'll just use to 2 decimal places, 0.71 and 1. Plus k2 e to the lambda 2t, which is 2.12, positive 2.12, times v2, which is negative 0.71 and 1. So we know that x of t and y of t are the top and bottom components of the y vector. And so if I now multiply this in, I'm going to have 0.71 times k1 e to the negative 2.12t. And so that's all I've done here is just this component right here times the k1. And now for y of t in the bottom, I'll have 1 k1 e to the negative 2.12t. Now for the second term, I'll have plus, here I'll have k2 e to the 2.12t times negative 0.71. So minus 0.71 k2 e to the 2.12t. And then for my second y term, I'll have plus 1 k2 e to the positive 2.12t. So I have my x of t as the top equation, my y of t as the bottom equation. We've said in this problem that we're going to let the initial condition for x at time 0 is 500. The initial condition for y at time 0 is 600. And so we now can set up our, solve for our initial condition. So 500 is x. So we'll have x of t is 500 equals 0.71 k1 e to the 0, right? Because e to the negative 2.12 times 0 is e to the 0, and that's just going to be 1. So that's the cool part about solving these is basically e to the 0 is going to be 1, and so in each of these terms we're just left with the k coefficients. So minus 0.71 k2, again all I've done is plugged in 0 for t up here, and the second equation will be 600 equals k1 e to the 0, which is k1, plus k2 e to the 0, which is plus k2. And now I want to solve this, so we're going to use Wolfram alpha to do it for us. I've already have that here. 500 equals 0.71 k1 minus 0.71 k2, comma, 600 equals k1 plus k2. The solution I get is k1 is 652.113, k2 is negative 52.11. And going back to our x of t, I'm going to replace k1 and k2 with their respective values. Same thing for y of t. Replace k1 and k2 with their respective values. So 0.71 times the 652.11 minus 0.71 times negative 52.11. I'll multiply those two pairs of factors together. Gives me 463 and 37. And then since the second equation is just k1 e to the negative 2.12t, I'm just going to plug in 652.11 there, and now I'll have plus k2 e to the 2.12t, which is negative 52.11 e to the 2.12t. So there's my solution. I can now go over to Desmos and graph these. Well, part of the question was, what's going to happen? Solve the system and produce graphs of x of t and y of t. And here's what goes on. So the red curve is the species 1, the blue curve is species 2, and what we see is that species 1 starts to decay immediately. Well, they're being eaten, so that makes sense. But species 2 is being eaten at a much faster rate than species 1. Going back up to our model, species 2 is being eaten at 3, at a rate of 3 of them per prey, or per x, and so we see that one fall off until at about time 0.596 days, we see that species 2 becomes extinct. Now it looks like species 1 is going up, but that's only because our y values become negative, And so dx dt, because it's equal to negative 1.5y, it looks like it's going to go back up, but you can't eat negative species 2. So really we have to say after t equals 0.596 days, species 2 is extinct. It does not make sense to consider anything that happens after that time. So we've solved that one. Let's look at one more. Suppose we have two species, each one preys upon the other, and also let's say that species 1 reproduces at a rate of 30% per day and species 2 at 120% per day. So not only are we going to now have our two original terms in the equation, but now dx dt is still going to equal negative 1.5y, but also x is going to reproduce at a rate of 30% per day. So 30% of whatever it currently is going to add to our x population. It's going to increase it at a rate of 30% per day. dy dt is going to equal its original negative 3x, but it reproduces at a rate of 120% per day, which is 1.2 times the size of that population. And here, notice that my y term is first and my x term is second, so I should rewrite it as 0.3x minus 1.5y. And this one's good, that one's negative 3x plus 1.2y. And so this leads me to grab my coefficient matrix, which is 0.3, negative 1.5, negative 3, and 1.2. So now I'm prepared to find the eigenvalues. This is a first order homogeneous constant coefficient linear differential equation that matches that form ax plus by cx plus dy, where a, b, c, and d are all constants. If a, b, c, and d are not all constants, this method won't work. So here I've just entered those values into Wolfram Alpha. Wolfram Alpha recognizes the same inputs that I gave it, so that's good. And I come up with my lambda 1, lambda 2, v1, and v2. So that means that y, my solution, is going to equal k1 e to the lambda 1t, so 2.92 t, times v1, which is negative 0.57 and 1, plus k2 e to the lambda 2t, which is negative 1.42, times v2, which is 0.87 and 1. So again, I'm going to parse this up into the x solution and the y solution. And so again, I'm going to just distribute this into the vector. So I'll have negative 0.57 k1 e to the 2.92t plus k2 e to the negative 1.42t times 0.87. And I'm going to do the same thing for the bottom row. That'll be 1k1 e to the 2.92t plus k2, 1k2, so k2 times 1, e to the negative 1.42t. And now I'm going to plug in my initial conditions again. So x was 500 at time 0. So e to the 0 will be 1, and I'll just have negative 0.57 k1. E to the 0 will be 1, so I'll just have plus 0.87 k2. And same thing down here, but 600 equals 1 k1 e to the 0 plus 1 k2 e to the 0. And now I need to solve this system right here. So to do that, I will plug this into Wolfram Alpha to solve this system for me. So here we have the first equation, comma, the second equation. And we end up with a solution of k1 is about 15.28, k2 is about 584.72. So in the first equation, I'm just going to replace k1 and k2 with those values. So here we have 15.28 and 584.72. Same thing for y of t, 15.28 is 1k1 584.72 is 1K2. And now I'll multiply these coefficients together to get negative 8.71 and 508.71. I can now graph these two equations, and I see something similar, except now notice that species 1 dies off, and that might be explained by the fact that they don't reproduce as rapidly, and population 2 is really thriving. So we see that eventually population 1 becomes extinct at time 0.937, which that's the time that we have to stop this model, because it doesn't make sense to be using negative x values and causing the second population to rise because of that. There's a little bit of a rise because the species 2 is thriving, but after time 0.937, it doesn't really make sense what we see there. So after t equals 0.937 days, species 1 is extinct. It does not make sense to consider anything that happens after that time. We could also look at the phase plane for this model to see kind of just what's going on in general. Let's do that real quick. So here we have our original grapher. And here I have those equations input in. It doesn't matter what order you put the terms in, but don't forget those multiplication signs. And for x, I'm going to look at x from about, let's say, 0 to 600, and I'm going to look at, that's y. Y is going to go from about 0 to 600. Let's make that a little bit higher to 700, and let x go from 0 to, we'll say, 600, since that would cover our initial conditions. It doesn't like to really graph this very well. Let's try something closer to our initial values. And anywhere in here, you can kind of see that the x population is always moving to the left. It is on the fritz. It is going to die off. So let's plot y from 0 to 600. And you can see that that's the population dying off. That's exactly what we saw in our solution curve. And let's plot x from 0 to I think 500 was our initial condition, so let's go ahead and do that. And there's our curve corresponding to that. And you can see that regardless of what initial condition we pick, there are some where the interchange is actually different. You can see here for this initial condition, it's actually x of t that's dying off and y of t that is thriving. But we can also cause that to switch gears if we reduce the size of y, but we keep the value, initial value of x the same. We can get some pretty cool stuff. And we'll talk about this in another video session where we'll try to understand what's going on here. So in one final video, we'll just go ahead and prove that this solution system theorem works. But we'll go ahead and stop here with our discussion of solving first order systems.